Hello students, welcome back to JCE Connect series of lectures. So in previous lecture we have solved one numerical problem on velocity triangle. So we'll continue with one more problem on a velocity triangle. So that is a numerical problem on velocity triangle. So here the problem given as this problem. So let us take this problem. A jet of water having a velocity of 40 meter per second strikes a curved vein which is moving with a velocity of 20 meter per second. The jet makes an angle of 30 degree with the direction of motion of vein at inlet and leaves at an angle of 90 degree to the direction of motion of vein. At outlet, draw the velocity triangles at inlet and outlet and determine the vein angles at inlet and outlet so that the water enters and leaves the vein without any shock. So this is the problem given here. So first write the given data. The velocity of jet is given 40 meter per second, velocity of vein at inlet is 20 meter per second, angle made by the jet at inlet is alpha is 30 degree. Then angle made by leaving jet is 90 degree. Okay, so with this, so angle made by the leaving jet at 90 degree, so the beta is 90 degree here. So next draw the velocity triangles. So let us draw this first velocity of jet, then the vein is moving in this direction u, then that you shift and keep here, then this will be u1, this shows the direction of vein, this is the jet direction, then the difference of these two will be the relative velocity vr1, then the component of v1 will be vw1, that is velocity of whirl and velocity of flow. So these are the two components of v1. So this will be v1 cos alpha and this will be v1 sin alpha. Okay, then the relative velocity will be making an angle of theta. This theta is nothing but vein angle at inlet, this equal to this. Okay, then triangle ABD represents the inlet velocity triangle. Okay, and this alpha is the guide blade angle or angle made by the v1 with the direction of motion of vein. Okay, so this is the inlet velocity triangle. First you need to construct this velocity triangle. After that, as the jet enters the vein passage like this and glides over the surface, and it is leaving by making an angle of 90 degree. It has been given in a problem. So here given, see, look at the way that jet leaves at an angle of 90 degree. At an angle of 90 degree. Okay. So in this one, so here this is the vein and the jet is leaving by making an angle of 90 degree. Okay, so if it is this is 90 degree, then this beta becomes 90 degree. Okay, so when beta becomes 90 degree, the vf2 is equal to v2. Then the whirl velocity here, the vw2 will be 0. The whirl velocity at outlet will be 0. Okay, then this represents the direction of vein motion. This u2, then this is the vr2, then this triangle EFG is a 90 degree triangle, that is right angle triangle, and this angle is pi, this also pi. Okay, then once we construct the inlet and as well as outlet velocity triangle is depending upon how the jet is leaving the vein, whether by making an angle of 90 degree or less than 90 degree or more than 90 degree, that you have to identify first. Based on that, you have to draw the outlet velocity triangle. In this case, the jet is leaving by making an angle of 90 degree hence beta is also become 90 degree. So here the beta angle is 90 degree. Then for this problem, u1 is equal to u2 equal to u, that is 20 meter per second. The vane angles at inlet and outlets are theta and pi respectively. Then from triangle BCD, this is from inlet velocity triangle BCD, BCD. So apply tan theta equal to BD by CD, then VF1 by VW1 minus U1. So what is VW1? VW1 is nothing but the component of V1, that is V1 cos alpha, and V1 is given, alpha is given, substitute and get the value, that is, this is called whirl velocity at inlet. Then VF1, V1 sin alpha, that is a component, that is a vertical component of V1 sin alpha, then that 20 meter per second we get. Then U1 is given, then also tan theta is equal to 20 by 34.64 minus 20, it gives 1.366. So in the theta you get, this is theta 53.79 degree. Okay, then further this is the inlet velocity triangle. Then calculate outlet velocity triangle. Here from triangle BCD, once again the refer inlet velocity triangle. Sin theta is VF1 by VR1, then VR1 you will get 24.78, but VR1 is equal to VR2 because the passage of blade is assumed very smooth, there is no frictional loss, hence VR1 is equal to VR2. Then this one, then refer outlet velocity triangle, triangle EFG, this one. So refer outlet velocity triangle, triangle EFG, this one, EFG, refer this one. Then from the outlet velocity triangle cos pi u2 by VR2, because VR2 we know, we don't know the cos, what is the angle, so from this we get outlet vane angle. So this is the way outlet vane angle. Okay, this is one simple problem. So let us take one more example here. A jet of water having a velocity of 45 meter per second impinges without shock in a series of vanes moving at 15 meter per second. The direction of motion of vane is inclined at an angle of 20 degree to that of jet. The relative velocity at outlet is 0.9 of that at inlet, and absolute velocity of water at exit is to be normal to the motion of vane. Find the vane angles at inlet and outlet. Work done on vanes per Newton of water supplied by the jet and hydraulic efficiency. So here first try to understand the problem and also what are the data given here. So here the data is given here, velocity of the jet is given, means from the nozzle the jet is coming with a velocity of v1 45 meter per second, and velocity of vane, once the jet hits the vane like this, the vane here, the nozzle is been fitted like this. So from this nozzle the jet is coming out and it is striking the vane. Okay, so v1 is given absolute velocity before striking the vane 45 meter per second. So when it strikes the vane starts moving, that is the vane velocity u is given, that is u1 equal to u2 equal to 15 meter per second, and angle made by the jet at inlet with the direction of motion of vane means this one, this angle made by the jet with the direction of motion of vane, that is alpha is also given, that is 20 degree. Then the relative velocity at outlet, in this case the relative velocity at outlet means whatever velocity with which the jet is striking at inlet, that is VR1, but when it glides over the surface because of the some losses, so at outlet the relative velocity is only 90% of inlet relative velocity. We are getting only 90% here, hence VR2 is 0.9 VR1, it is given in a problem. Then vane angles at inlet and outlet. Vane angles at inlet and outlet are theta and pi as usual. Then you have to construct the velocity triangle first. So draw V1, draw U1, then VR1, join this one, and alpha is the angle made by V1 and theta is the angle made by VR1. Then VW1 will be the component of V1 in horizontal direction, and VF1 is a component of V1 in vertical direction. VW1 is a whirl velocity, VF1 is a flow velocity, then theta is the vane angle at inlet. Similarly, at outlet, the jet is leaving the vane by making an angle of 90 degree, that is V2 equal to VF2. Hence VW2, that is whirl velocity, will be 0 here. So in this case, because the jet is leaving the vane by making an angle of 90 degree, hence beta is also 90 degree. Then this is the vane velocity. Vane velocity is at inlet tip as well as outlet tip, both are moving at same velocities. U1 equal to U2 equal to 15 meter per second, and this is pi, this is also pi. Then let us name the triangle EHG. Okay, so once you draw the velocity triangle at inlet and outlet, then you can easily calculate the vane angles at inlet and outlet. Just to apply the trigonometric function, that is in triangle BCD at inlet velocity triangle, tan theta equal to BD by CD. Just refer the triangle BD by CD. BD by CD, VF1 divided by AD minus AC, then VF1 divided by VW1 minus U1. So this is VW1 minus U1, you will get this one. Then where VF1 is equal to V1 sin alpha, 15.39 meter per second. Similarly, calculate VW1, V1 cos alpha, then 45 cos 20, then 42.29 meter per second. Then tan theta is 50, calculate tan theta, substitute here and you will get this one. Then theta you will get 29.42 degree, that is inlet vane angle. Again from triangle BCD, once again you calculate from the BCD. So we need to calculate what is VR1. So once we get to VR1, then we can easily get the VR2 at outlet. So with that intention, you have to refer again triangle BCD, apply sin theta VF1 by VR1, then calculate VR1. VR1 is VF1 by sin theta. Then get sin theta VR1, this much is the VR1, but at outlet VR2 will be 90% of VR1. You will get 28.2 meter per second. Then refer outlet velocity triangle, triangle EGH. We have cos pi equal to U2 by VR2. Then 15 divided by 28.2, you get this much. Then cos pi. Then you will get the vane angle at outlet, 57.87 degree. And they asked also work done on vanes per Newton of water, that means per weight. So work done per second per Newton of water striking. This is the formula. So we know that is 1 by G into bracket VW1 U1 plus VW2 U2. This is the formula we are having. But U1 equal to U2, and also whirl velocity at outlet will be 0. Because the jet is leaving by making an angle of 90 degree, the whirl becomes 0 there, and U1 equal to U2 equal to U. Then finally we get 1 by G VW1 into U. Then substitute here, you will be getting 64.66 Newton meter per Newton second, or joule per second by per Newton. This is a work done per second. Then efficiency is what? Output by input. Output is work done per second, and input is kinetic energy per second. And output, we know the formula output, VW1 plus VW2 into U, then divided by input is V1 square by 2G. And this V1 square by 2G, this is for a series of vanes. So this, whatever the equation we have taken, this is for series of vanes. Because so look at this, efficiency is work done per unit weight, then kinetic energy per unit weight. So work done, how we write? Fx into U. Then this will be V1 square by 2G. Okay, so V1 square by 2G. This is per unit weight. Weight is what? Weight can be written as M into G. Okay, then m into g, this will be what? Weight per second. Again, per second, what we write here? Rho a v square into g. Rho a v square into g. But kinetic energy per unit weight. Kinetic energy per second per unit weight. When you write half mv square, but per unit weight. So when you take a per unit weight, you divide this one, you will be getting this one. Okay, kinetic energy per unit, this divided by this one. Okay, so again mass per second. So means when you take kinetic energy per second, that is rho a v cube, we get kinetic energy per second divided by this one per unit weight, rho a v square into g, but half. This get cancels, one velocity get cancels, sorry, half mv square we got. So once we get this one, we get half v square by g. Okay, so we get that one here, v square by 2g for a series of vanes. Substitute here, you'll get the efficiency. Okay, so this is a simple problems. So please solve this kind of problems, and very simple. Only you have to remember how the jet is leaving the vane. So refer any textbooks. So solve the problems given in the textbook. Practice solved problems only. You will understand in a better way. Thank you.